In this lab, I observed Faraday's law by dropping a bar magnet down a tube of aluminum foil. I created a computational model of the forces involved in this experiment and compared my results. I found that I had significant error as my computational model results were very different from what I expected and those I calculated experimentally. To understand what is happening to the magnet as it falls through the tube, I used this equation for magnetic force on a loop by a falling dipole. As the bar magnet falls through the tube, the magnetic flux increases. So nature counters this increase by inducing a current that creates a magnetic field whose force on the magnet opposes the magnet's motion. This is understood by Lenz's law and Faraday's law. Finally, to understand the change in velocity and position, I used Newton's second law, which relates net force to total change in momentum over time. These are the specifications of the aluminum foil and bar magnet I used. I added these to the GlowScript code for the model. I dropped the bar magnet with the south pole going first through the tube and calculated the time it took for the magnet to fall out. These are the results of the experiment. The magnet spent a total of 1.2 seconds in the tube on average across 6 trials. To make the computational model, I added the specifications I listed previously. Here are a few of the important parts of the code. The first part is a function I will use later to calculate the magnetic field of a dipole. The next part is a function to calculate the change in flux over change in time. This is based on the equation explained in video 43. The next part is a while loop for the bar as it travels through the tube, so the time it takes for it to travel through can be calculated. I also added the gravitational force below. The ring's induced current is calculated in this line based on Faraday's law with the negative delta flux divided by the ring's resistance calculated earlier. Below that, I calculated the magnetic force on the magnet due to the ring, which is the induced magnetic force due to the induced current. Finally, I calculated the net force on the magnet. Using Newton's second law, I updated the velocity and position of the magnet as it travels through the tube as well. These are the results. On the left is the tube with the magnet and the currents in opposite directions represented by blue and red. On the right, you can see the total time in the tube is calculated to be 6.132 seconds. Because I dropped the magnet with the south end entering the tube first, the magnetic field induced in the ring should point in the negative y direction by Lenz's law. Using the right-hand rule, the current viewed from the top should be going clockwise, so the blue, which is on top, represents the clockwise current. The red should represent the counterclockwise current. If I flip the magnet so the north side enters first, the direction of the induced magnetic field would be reversed because the direction of the dipole's magnetic field would be reversed. As a result, the induced current would be counterclockwise from the top. There would be no change in magnitude. The computational time is very different from the experimental time and does not make sense. The magnet should not spend 6 seconds in the tube. Something went wrong here. Most likely there is some mistake in my code, but I could not figure out what it was. It is possible that the magnetic dipole moment I used for my calculations in lab 3 is not correct and could be skewing my data. To make the computational model more accurate, I could recalculate the magnetic dipole moment to make sure I'm using an accurate value. I could also account for air resistance since the magnet is moving through the air as it falls through the tube. For the velocity versus time graph, I learned these things about the forces acting on the bar magnet. In the section highlighted in green, the velocity is 0. This is when the net force is 0 and is at the moment I let the magnet go from rest. The blue section has velocity rapidly increasing in magnitude in the negative direction. In the red direction, the magnet has entered the tube. In the red section, the magnet has entered the tube. At this point, the induced current and magnetic force are acting on the magnet opposite to the gravitational force on the magnet. As a result, the magnitude of the velocity decreases. In the orange section, the net force on the magnet is 0 because velocity is not changing. At this time, the velocity is still negative, so the magnet is falling down. Once the magnet leaves the tube in this last blue section, the net force is only the gravitational force acting on the magnet, so the velocity is increasing in magnitude and is negative again. If the resistivity is decreased, the current will increase. An increased induced current would lead to the induced magnetic field also having a larger magnitude. the magnetic force of the ring on the dipole would increase, so the magnet would have a decreased velocity. So as a result, the magnet would take longer to fall through the tube. Holes would interrupt the flow of current, which would disrupt the strength of the induced magnetic force. As a result, the magnet would fall out of the tube faster than it does now and would take less time to go through the tube.